In lesson 9.1, conics and calculus, we're going to pretty much explore all there is that we need to explore concerning conic sections. Now, before we get into any of the algebra, any of the graphs, or any of the manipulations of conic sections, we should first explore what they are and where they came from. Now, luckily, we're not going to make conics quite as difficult as it used to be, as you see here. This is actually the table of contents of Cyclopedia, or a Universal Dictionary of Arts and Sciences. This was published in 728 in London by Ephraim Chambers. Conics, it can be confusing, but let's not do that. Rather, let's take a look at this animation right here. Now, you'll notice that really the way that we form conics are by chopping off pieces of a cone, or in the case of a hyperbola, a double cone, which I'll show you in just a moment. But depending on which angle we form that cut, we could get a hyperbola, a parabola, an ellipse, a circle, or even if you chop it right at the intersection of the two cones, we could even get a point. So that's where the conics come from. They come from the cone. In fact, just think about the word conics. It describes a cone. Here's an image real quick where you can see the four major conics and how they're formed by a sheet of paper, if you will, a cross-section, which is why we call them conic sections, in fact. So you can see that when the section cuts the double cone, depending on how it cuts it, we get these different conic sections. Now, it's simple enough to say, okay, these are shapes, but the shapes have some very, very, very important features to them. We're going to look at things like the focus, or foci in the case of there being more than one. We're going to take a look at the directrix in the case of a parabola, or the eccentricity, regardless of the conic section. We'll take a look at how to graph all these, and finally, we'll do a little bit of calculus to find the lines that are tangent to certain conics at certain places, and things like that. So, all that being said, why don't we begin our study of conics by looking at the parabola. This graph here is the standard representation of the conic parabola. This particular conic section takes on the equation x minus h squared equals 4 times some value of p that we'll discuss in a moment, times the quantity y minus k. This is the standard conic form of the parabola equation. So there's a lot of letters here and a lot of features in the parabola that we need to cover. The first thing I want to make notice to you is this orange point right here, which we call the vertex. The vertex is the point, if you will, of the parabola. It's where the parabola stops going one direction, starts going the other, or it's the extrema of the parabola, however you want to look at it. We call this the vertex, and it is h comma k. Now notice that that is simply the transformation of the x and y variables according to the parabola equation. So no big deal, h comma k. Once you find that vertex, there's a couple ways you can go from here. If you go down, if you go up the value of p, you'll get to what we call the focus. So the focus is clearly going to have, it's going to be a point that is h comma k plus p. That p really doesn't have a name. We generally just call it the p value. And when you rise up p, or rather when you add p, you get to the focus. Now what if you were to subtract p? If we were going to go down, that would bring us to our directrix, which is this black dashed line. So that's going to have the equation y equals k minus p. And it will always be y equals k minus p for our directrix, just like it will always be h comma k plus p for our focus. Now, there certainly is a focus directrix definition of the parabola. I'm not going to get into that here, although I certainly invite you to look that up. It just basically has to do with the length of the line segments that go from the focus to any point on the parabola, and then that point to the directrix. So it is a focus directrix definition. Certainly look it up. It's something that you should know. I'm just not going to get into it here. So we have the vertex, we have the focus, we have our directrix, and the last thing we need to discuss is the line segment that connects these 2 points on the parabola. That line segment is called the latus rectum. And if you take Latin or any of the Romantic languages, latus rectum, you should be able to translate that yourself. If not, again, I certainly invite you to look that up. But what I do want you to know is that the length of the latus rectum, which I'm going to abbreviate LR, the length of the latus rectum is simply the absolute value of 4p. So this p-value is very important. It tells us how far the focus is from the vertex. It tells us how far the directrix is from the vertex. And finally, it tells us how long that latus rectum is. Now, let's take a look at what would happen if our p-value decreases. So, that was pretty cool. Did you notice what happened when p equals 0? The parabola became degenerate. It became a flat line. Probably happened too quick for you to notice, but just understand, p can't be 0. P can't be 0. Think about it this way. Our vertex is still going to be h comma k. Now that p is negative, we're still going to add p to get to the focus. Why is it going down? Because p is negative. And in fact, we're still going to subtract p to get to our directrix. We're still going to say y equals k minus p. Of course, p is negative now, so we're actually going to go up to get to the directrix. And fortunately, the latus rectum always was just the absolute value of 4p, so nothing's going to change there. But just imagine if p were 0, what would happen? The vertex, the focus, the directrix, they'd all end up in the same place. And how long would the latus rectum be? It would be 0. Would not be a very exciting parabola at all. So what would happen if our parabola were actually a sideways parabola? You really could just tilt your head and just repeat all of the last stuff and kind of figure it out for yourself. But let's real quickly just run through it. You're going to see a lot of similarities. Parabolas are easy and nice for that reason. And so here is our what I'll call sideways parabola. Again, all the same measurements, all the same, pretty much everything, really. The big difference here is going to be that this is a situation where the y term is squared. So we'll have y minus k quantity squared. Again, we'll have the 4, the p-value, and x minus h here. So just like before, our vertex right here is going to be known as h comma k. And just as before, when we add p to that, that will bring us to our focus, which in this case is now h plus p comma k. If we subtract p, we'll get to the directrix. Of course, notice that the directrix is now a vertical line, so it's not going to be y equals. This time it will be x equals, and it's going to be x equals h minus p. Again, when p is positive, it's going to look just like you see here. When p is negative, it will flip around and open up the other way. But all of these formulas are still intact. Finally, we have the latus rectum. Remember, that is the length of this line segment right here, which basically controls the width of the parabola. And just as before, that will be the absolute value of 4p. Now, again, when p is positive, it's going to open up to the right. When p is negative, it'll open up to the left. And with all that information, why don't we go ahead and take a look at our first couple of examples here. In our first example of this chapter's notes, we're given this standard form equation, and we need to write the equation in a standard conic form, that is with the 4 and the p and all that good stuff. Now, the first thing you'll notice, I hope, is that only the y term is squared. There is no x squared here, and that tells us that this is a parabola. Furthermore, because it's the y that's squared, it tells us that the parabola is going to open left or right. So let's just go ahead and do some math here and see how this works out. To turn this into standard conic form, what we need to do is a little bit of completing the square. So I'll take all the y terms and leave them on the left side of the equation. I'll move all the x terms and the constant to the right side of the equation so that we have something like this. Now, what I'm going to have to do here is to complete the square. I'm going to figure out which number I need to place there, and I will follow that up by placing the same number over here to the right. So, that shouldn't be too much of an issue to complete this square. Hopefully you can tell real quick that I need a 9 that's half of 6 squared, would give us 9 here. So if I'm going to add 9 to the left, I better add 9 to the right. And let me go ahead and do some simplifying here. This will be y plus 3 quantity squared. Over here, I need to pull out a 4 and a p. So what would be easier? My suggestion is to pull out the 4 first. So if we pull out the 4, what I'm left with in here is negative 2x. This would be 21. Now it's going to be 21/4. All right, we're almost there. The trick of this, an easy way to find p, is that the x term cannot have a coefficient on it. Cannot have a coefficient. So whatever coefficient it does have, I'm going to pull that out, and that's going to become the p. In this case, that's going to be the negative 2. Now, in a situation where the x already doesn't have a coefficient, then you're actually just going to pull out a 1, and your p will be 1. That does happen, so be on the lookout for that. Anyway, so this is going to be my standard conic form of this parabola. Let's see how much information I can garner from this equation here. First off, I do want to find my vertex. That's the point that everything else is built off of. And in this situation, hopefully you can just look and see that my vertex here will be 21/8, comma, negative 3. 21/8 is not happy, but it is what it is. So 21/8, comma, negative 3. Let me go ahead and put that down here and see where that goes. So it looks like my vertex is going to be about right here on my graph. All right, so far so good. To find my focus, remember that for the focus, all I need to do is add whatever p is. So if I do that, if I add p, let's see here. Do I know what my p is? Sure, I know that p is negative 2. I'm going to go ahead and just make a quick note to myself of that fact. So if p is negative 2, that's great. If I add that to my vertex, let's see here. That's actually going to give me 5/8. By adding that negative 2, I actually need to subtract 2. So there you go. And it looks like my focus is going to be 5/8, comma, negative 3. That's about right here, let's say. All right. So far, so good. Let's see if we can find our directrix. And however I found the focus, the directrix is pretty much the same, except instead of adding p, I'm actually going to subtract it. That's going to bring me further to the right. And in fact, it's going to put me at x equals 37/8. 37/8, that's a little bit less than 5. And so I'm going to go ahead and draw a dashed line. And hopefully you can do it straighter than I can. But there's my directrix. So far, so good. Last thing I really need to figure out is how long my lattice rectum is. At this point, I can tell where my parabola is going to go. It's going to go up here and down here. But how wide is it going to get? That's what the lattice rectum controls. And here in this situation, whatever 4p is, the absolute value of 4p, that's my lattice rectum. In this case, that's going to be 8. So what does that tell me? I need to go 4 up from the focus. I need to go 4 down from the focus. And now I can see how wide my parabola is. I'm going to do the best job I can at drawing this. It's a little bit tricky, but... oh, that's not too good. But hopefully you can understand what it's supposed to look like. And there's our parabola. We just completed the square, put a standard form equation into standard conic form, found everything we needed to about the parabola, and graphed it. So, beautiful job there. Let's take a look at our second example. So for our second example, we have a rather common problem here, where they give us some aspects of our graph, and we actually need to come up with the equation that represents that conic section and its graph. So sometimes they're difficult, sometimes they're easy. It's just a matter of deducing the clues that you need to fill in the variables. So let's go ahead and take a look at this. This is going to be a parabola with its vertex at -1, 2, and I'm going to go ahead and put that there, and a focus at -1, 0. Now, what can I tell from this immediately? Well, if I take a look at this distance right here, remember that this is going to be p, all right? And so I can tell that p is going to be either 2 or -2. Well, if this is our focus, it should be clear that this will be opening down. And so this must be p going down then. We need to be careful about that when we make our equation. So let's go ahead and also, if we want to graph the whole thing, not that it asks to, but If we go up a value of p, that will bring us to our directrix, which is right here then. Clearly, this is the line y equals 4. All right, so we can see that p is, again, 2, some value of 2. If I want to continue graphing this real carefully, remember that my lattice rectum is going to be 2p in each direction. So if I go 2p this way, I'll end up here. And if I go 2p this way, I'll end up here. So here is going to be the actual graph of my parabola. It's going to look something like this. Actually, it's going to look a lot better than that, but there's some version of it anyway. Because this is opening up or down, you should be okay with the fact that this is going to be an x minus some quantity squared type problem. That will equal 4 times our value of p, and then we'll have y minus whatever that center comes to. So we were told that our vertex was negative 1, 2. Remember, that's h comma k. H comma k is our vertex. So there is going to be our h. It's going to be negative 1. K will be 2, so I can just go ahead and fill these in. If h is negative 1, that's actually going to make this x plus 1. This will be y minus 2. And if it were opening up, we'd have a positive p. We're opening down, so this must be a negative p. And as we said before, the p value is 2. So here is going to be our equation for this parabola. See, sometimes it's easier to graph what you're given and try to work out the rest. Sometimes it's easier to do it algebraically. It just depends on A, the type of problem, and B, whatever you are more skilled at. So just takes practice, and of course we have a homework set coming up, so you'll get that practice. Anyway, all this being said, why don't we begin our exploration of ellipses, see what those things look like here. For the next set of problems, we're going to be dealing with ellipses. Now, what are ellipses, you might ask? Ellipses are simply conic sections that have two foci, and both of those are internal to the graph. If the foci were external to the graph, that would be an entirely different shape, and we'll be getting to that later. We've dealt with parabolas that have just one focus. I will tell you that circles also only have one focus, or you could think of it as an ellipse with foci that are in the same location, if you want to think about it that way. But here is our standard graph of an ellipse. This is a sideways ellipse, and the way that these are expressed in algebraic form, we'll have our x plus h squared, and we'll have our y minus k squared, and that might start to look a lot like a circle, but what we're going to do is we are going to put different denominators under our x and y terms. So we'll have an equation that looks like this. Now, how do we know whether the ellipse is going sideways or up and down? You see that it's a sum, so it doesn't really matter which order it's written in. It's going to be the same graph. So what we need to do is look at the denominators. And whichever denominator is larger, that signifies what direction the ellipse is going to be going. In this particular case, we're going to deal with the situation where A is larger than B. In other words, this is the large one in the situation we're dealing with here. So let's take a look at some information that hopefully some of it is obvious by now. We will have a center on our ellipse, and that center will be h comma k, coming from the x and y components of our equation there, h comma k. Now the good news here is finding the vertices and what we call the conjugate vertices is actually fairly easy. This line right here, this line segment I should say, has a length of a, and that means that going backwards it would have a length of a as well. What that means is to get to our two vertices, and the vertices, by the way, are always on the major axis. They're the ones that are further from the center. So on a sideways ellipse, the vertices are sideways. On an up and down ellipse, the vertices will be up and down. But anyhow, this point right here, we're going to call this point h plus a comma k. My apologies if that's kind of hard to read. But that's h plus a comma k. This other vertex right here, let's see if I can write it this way. This would be h minus a comma k. So that's a little bit tricky to write, but there you go. So our two vertices we can find by simply adding and subtracting a from the x value of the center. Hopefully that makes some sense there. And those are the actual vertices. On my notes, which I've done earlier, I actually call the vertices h plus or minus a, comma k. And if I need to graph those, I can figure out what those are. Now, this segment right here has a length of b. And so what that means, these are called the conjugate vertices. They're the vertices that are on the minor axis. They're closer to the center. They're where the ellipse is flattened. And they're going to hold the equation h, comma, k plus or minus b. That one will be hk plus b. And this one, of course, then would be hk minus b. So those are going to be your conjugate vertices. And there you go. Now, in order to find the foci, finding the foci is going to be a little bit trickier here because this particular length is not something that's easily given in the equation. Rather, what we need to do is denote a new value that we're going to call c. And for an ellipse, c is simply going to be the square root of the absolute value of a squared minus b squared. The reason for the absolute value is even when the ellipse gets flipped so that it's actually going up and down, we can leave that formula for c since it's the absolute value. It doesn't matter which order we subtract them. So there you go. So the foci, to find the foci, we need to understand that the foci are a distance of c from the center. And so this particular focus here will be h plus c, comma k. That'll be this focus. And this focus over here will simply be h minus c, comma k. And that's everything that we need to know in order to graph an ellipse. The last thing I need to tell you about is the eccentricity of an ellipse. I told you that I was going to tell you all about eccentricity later. For an ellipse, the eccentricity is simply a value of c minus a if it's sideways, or c over b if it's up and down. It's basically just c divided by whichever denominator is larger, the square root of that denominator. So there is a sideways ellipse. Let's go ahead and very quickly take a look at what I'm going to call an up and down ellipse. So as promised, here is our up and down ellipse. Let me go ahead and rewrite the formula here. The formula is actually going to be exactly the same. There's only going to be one small difference. And if you couldn't already guess, the difference is going to be that b squared is going to be larger than a squared this time around. In other words, this is now going to be the larger number. Because that's under the y, that tells me that this is going to go up and down. When the larger number was under x, sideways was going to be the major axis. So that's the big major thing. Let's see how that affects everything. Our center will still be at h, comma k. Going sideways, we're still going to add a value of a. All right, a is still underneath the x, so that's still what we're going to add. So this will be h plus a, comma k, just like before. And also just like before, the other sideways vertex, which this time, these are the conjugate vertices because they are closer into the center. So our conjugate axes are going to be h plus or minus a, comma k. Our major axis vertices this time around, again, just like before, this is going to be b. So we'll have h, comma k plus b, and down at the bottom we'll have h, comma k minus b. All of this should be very familiar. Nothing there has changed. However, now it's time for perhaps the things that do change. I don't know. Just like before, we are going to define c as the square root of the absolute value of a squared minus b squared. Again, it doesn't matter that b squared is bigger this time around, because it's simply going to be the absolute value anyhow. And just like before, the focal distance, we're going to call it that, the focal distance is c. So this time, our focus is going to be hk plus or minus c. The plus c will be my higher one, and k minus c will be my lower focus. So last thing we need to talk about is eccentricity. Just like I told you with the sideways parabola, the eccentricity is simply, or I should say ellipse rather, the eccentricity is simply c divided by the larger of the two numbers on the bottom, or the major axis, if you will. So eccentricity now, C over B. And that being said, let's go ahead and do a problem similar to the very first example, but this time we'll notice that both x and y are squared, leading us to an ellipse. So for our first example with finding the equation of and graphing an ellipse, again, we're given the equation in standard form, and we need to turn it into conic standard form. So the way we're going to do that, just like before, we're going to work on completing the squares. For my x terms, I'm going to gather those together, but I am going to factor a 2 away from them. That's simply because the x squared term needs to have no coefficient in order to complete the square. So I will complete the square right here in just a moment. I'll see what I get when I do that. As far as the y squareds, I also need to factor something out of the y squareds. Because there's nothing to factor from y squared, I'm just going to pull a 1 out, and that will leave me with this. Of course, I will need to complete this square as well, and I'll do that here in just a moment. So, what is this all going to equal? Well, if I move my constant to the other side, that would be 3.12. So, what numbers am I going to use to complete these squares? Half of 2.4, 1.2, and if we square that, we get 1.44. So I'll add that here. Now, don't add 1.44 to the other side. Be very careful, because what we actually just did is added two 1.44s over here. To compensate for that, I'll add 2.88 to the other side. Now, to complete this square, half of negative 6.4, that's negative 3.2. And then, of course, when we square 3.2, we'll get 10.24. That I'll fit right there. That time, there is only one of those, so I don't need to do anything tricky here. It's just going to be 10.24. So, when I work all this out, this is going to say 2 times the quantity x plus 1.2 squared. This will just be 1 times the quantity y minus 3.2 squared. And this over here, if I do my math correctly, should just equal 10. So that's pretty friendly. Now remember, the ellipse equation says equal 1. So I do need to divide everything here by 10. And when I do that, I'm going to get my final conic standard form equation. I'll have a 5 on the bottom of the x term. And if I divide over here, it looks like I'm going to have a 10 on the bottom of the y term. And now it equals 1. So everything is good. All right, well, that being said, let's go ahead and see what information we can get from this. Let's start with our center. After all, everything really needs to start with the center on these graphs. And hopefully it's easy for you to tell that the center is simply negative 1.2, comma, positive 3.2. That's just coming from the h and k. So if I go ahead and graph that here, negative 1.2, comma, 3.2, looks like my center is going to be about right there. All right, well, let me go ahead and deal with my vertices next. First off, I need to ask myself, is this going to be a sideways ellipse or an up and down ellipse? And for that, all I need to do is look at the standard form conic equation, say which one has the larger denominator. Clearly here, y has the larger denominator, so this is going to be an up and down ellipse. And in fact, I'm going to go up the square root of 10, and I'm going to go down the square root of 10 to get to my actual vertices. Now, I actually worked this out earlier, and if I go up the square root of 10, I'll have a y value of about 6.3, and if I go down, I'll have a y value of just over 0. So that's what that's going to look like. Now, how do I write these vertices? They're going to be negative 1.2. What I'll have here is 3.2 plus the square root of 10. That'll be one vertex, and then the other vertex will just be 3.2 minus the square root of 10. And you can check those for yourself, that is where they belong. All right, the conjugate vertices are also not too difficult to figure out. For those, I'm just going to go the square root of 5 to the left and right from the center. So I did that earlier, and I got values of negative 3.4 approximately and 1.1 approximately. Now, I could write those here, but if I want to be a little more exact about things, which I do, I'll go negative 1.2 plus the square root of 5, comma 3.2. And I think you know what the other conjugate vertex is going to look like. It's just the plus and minus. So there are my vertices, my conjugate vertices. All I'm really missing here is my foci. And to do that, all I need to do is a little c equation. Remember that c is going to be the square root of the absolute value of the difference of these. So I can call that 10 minus 5. Doesn't really matter what order I go. And so my focal length is going to be the square root of 5. Let me go ahead and write that down here then. My foci, well, I'm going to go up the square root of 5. That's going to take me to about right here. And let me go ahead and make that blue. And that's also going to bring me down to about right here. So those are my foci. And if I want to write those down here, which I do, negative 1.2 comma, remember it's all based off of the center. Everything is based off of the center. That's why you will always see me do the center before anything else. So there are going to be the exact locations of my foci. Now I can go ahead and attempt to graph this. That is always the hardest part for me. This one isn't half bad, but it's only half done. All right. So I kind of missed the conjugate axis here, and it's kind of flat over here, but that's not too bad. The last thing I want to do is look at my eccentricity. Eccentricity here is actually going to be very easy. It's simply C over B. C over B. So here is C, and B is going to be the square root of 10 here. And so it looks like my final eccentricity is the square root of 1/2, which we can call about 0.707. I will invite you later to check out what different eccentricities mean to these conics. That eccentricity of 0.707 does tell me that this conic has to be an ellipse. Well, let's take a look at one more ellipse example before we move on. This next one, I can guarantee, will be fun and exciting. All right, so example D is one of those examples where they give me a bunch of information, and I have to find the equation for this ellipse. Well, since I know that this is an ellipse, before I even start graphing or trying to figure out anything, let me just go ahead and write the skeleton of my equation here. No matter where the center is, no matter whether it's going up or down or whatever the vertices are or anything, my equation is going to look like this. So I'll start with that, and I'll try plugging in things as I go along here. Well, the first and easiest piece of information I'm given are the vertices. Those are going to be 0, 2, and 4, 2. And I am given that those are the vertices, not the conjugate vertices, the vertices. So I know that this is going to be a sideways ellipse. I know that the bigger number is going to go in the denominator of the x fraction. So, first and easiest thing to do would be try to find the center here. And hopefully you realize that the center is midway between the two vertices. So this center is going to be 2, 2. And I'm going to take this opportunity to fill in my first two pieces of information here. Now, is there anything else I can figure out from the information I've run through so far? Well, I do know that from the center to my vertex is a distance of 2. Well, that's going to be real helpful. That's going to be my a value then. And of course, I need to put 2 squared under the x. So this will be 4. And I'm going to put it in blue here. Why not? So I have that, and all I really need to figure out is b. Well, if I was given the conjugate axes, I'd be able to just count and say, whatever that squared is, that's what I'll put under the y. Unfortunately, I'm not given that information. However, I am given an eccentricity, and I am going to use that fact. The eccentricity, which is 1/2, recall that that's simply the value of c divided by the major axis, which in this case is going to be 2. Well, this is real nice and handy. This tells me that c has to be 1. Now, do you remember the formula for c? Remember that the formula is simply the square root of the absolute value of the difference of the numbers on the bottom. So I'm going to write it kind of like this here. And if I have that, let me go ahead and do a little math here. If I square both sides, I'll have 1 equals 4 minus b squared. And you can do a little bit of math here. We'll get that b squared is 3, and so b must be the square root of 3. Now, of course, I didn't need to really go all that far, because it's the b squared that I needed anyhow. B squared is 3. Well, I'm going to go ahead and put that right there. And that gives me all the information I need. If I want to complete graphing this, I can. I simply just need to go up the square root of 3, and I'll write that here. That will be my minor axis length. And with all that information, I can draw my ellipse, or rather I can pretend to draw my ellipse. It ain't pretty, but there we go. That is the ellipse, and here is our equation. Now, all that being said, let's go ahead and take a look at the third kind of conic that we'll be examining here, and that is the hyperbola. So let's finish up our study of conic sections by looking at my favorite conic, the hyperbola. Now, the hyperbola works a lot like the ellipse. There's two foci. The way we get C is very similar. Just realize that this time, instead of the foci being internal to the conic, it's actually external. It's further away than the vertices relative to the center. So that's going to be the only real major difference. We'll also have to deal with asymptotes and things like that. But I'm going to show you a very easy way to graph these hyperbolas. Now, when we have a sideways hyperbola simply means that in the equation, the x term is going to come first. It doesn't matter which denominator is larger. This time it simply matters whether x or y comes first. So, a sideways hyperbola, like what you see here, is going to carry this equation with the x term first. Shouldn't be any surprise to you that the center of this hyperbola, although it's not really a part of the graph itself, the center is h comma k. Now, to find the vertices of this sideways hyperbola, we're simply going to add and subtract a to the x value of the center. So this vertex right here, we can call this h plus a comma k. That'll be this vertex. And this vertex over here will simply be h minus a comma k. So that's how we find our vertices. That's not very difficult. Although it's not on your notes and you don't really have to know this per se, I'm also going to tell you how to find the conjugate vertices. Those are the vertices that aren't actually part of the hyperbola at all. And these should also be no surprise if you understood what we were doing with the ellipses. This conjugate vertex will be h comma k plus b, while this conjugate vertex will simply be h comma k minus b. So that's how we're going to find our two vertices and our two conjugate vertices. Now, what's really helpful, once you find all four of those, you can actually create this box. You see it outlined here in orange. And this box is very, very helpful because it's going to help us to find our asymptotes. Now, we'll get to the foci and we'll get to the graph of the hyperbola in just a moment. But let's talk about these asymptotes. Of course, they are lines. Each one passes through this h comma k. And all we really need to find then is the slope of each asymptote. Well, if you recall that this right here carries a value of a, and if you also recall that this right here carries a value of b, then you should be able to see that our slope for this positive asymptote anyhow is simply going to be up b over a. And in fact, the equation of this asymptote is going to be y minus k equals the slope, which in this case is b over a times the quantity x minus h. So that's not entirely difficult. Notice the point h comma k is included in that asymptote, and our slope here is b over a. Now, what's the equation of this negative asymptote? It also passes through h comma k, and it, if you follow this box, has a slope of negative b over a. And so if I write this, I'm going to go ahead and write y minus k equals, and then the slope here is going to be negative b over a, and that'll be times the quantity x minus h. So now we have our vertices. We have our conjugate vertices. we've made this box in order to find these asymptotes. And once you draw these asymptotes, then it's very easy to draw the hyperbola, because the hyperbola simply needs to approach the asymptotes on both of its wings. Now, how do we find the two foci? That also is not going to be entirely difficult. Remember when we did ellipses, we said that c was the square root of the absolute value of a squared minus b squared? Well, we subtracted because those foci were inside the ellipse. Now, since the foci need to be outside the hyperbola, we're going to turn this into c equals the square root of a squared plus b squared. And so what that means, this focus right here is going to be h plus c, comma k. Of course, our c is already defined over here. And this focus is simply going to be h minus c, comma k. So that tells us pretty much everything we need to know. The last thing we need to cover is the eccentricity. And what I'll tell you is that on a sideways hyperbola, the eccentricity is simply c over a. Remember that a is our major vertex, or our major axis, rather. So again, our eccentricity, just like with ellipses, is the focal length divided by the major axis length, c over a. Now, we'll go ahead and flip this hyperbola so that it's opening up and down. But you should be able to fill in all the information. It's all very similar to this. So let's just go ahead and breeze right through that. And here is our up and down hyperbola. Now, I'm not going to spend a lot of time on this. Everything is going to run very similar to the sideways hyperbola, with the big exception that the y term is actually going to come first this time around. When I say comes first, what I mean is it's the positive one. If we always write the positive one first, then it'll be easy to tell which way our hyperbola is supposed to be going. So here will be our equation for this hyperbola. Notice that it's opening up and down this time. Of course, our center, just like it always has been, is going to be h comma k. I can still get to my conjugate vertices, similar to how I did before. Since I'm going sideways, those will be h plus a comma k and h minus a comma k. So no big difference there. And to get to my actual vertices, those will simply be h comma k plus b and h comma k minus b. Notice that nothing here is really different. In fact, all of that is the exact same no matter which way the hyperbola is opening. The only difference is which ones are the vertices and which ones are the conjugate vertices. But that you can simply tell by looking at what comes first in the equation. So, all that being said, we can still do our equation for the asymptotes. I'm still rising up b and running a. And let me just go ahead and mark that here real quick. From here to here, that is going to be b. That is my rise. And from here to here is a. That's still my run. And so my asymptotes are still going to be y minus k equals, this will be b over a times the quantity x minus h. That's going to be the positive asymptote. And if I want the negative asymptote, that's simply going to be y minus k equals the negative. That's going to be negative b over a times the quantity x minus h. So you can see that is still the same regardless of which way the hyperbola is opening up. Well, the last thing I need to deal with is the foci. And remember, just like before, our c value in this case, because it's a hyperbola, is just going to be a squared plus b squared. And what that means is that this focus is going to be h comma k plus c, and this focus will be h comma k minus c. So everything pretty much the same. It's just a matter of which way is the hyperbola opening. Of course, that's the way the focus needs to go. Last thing to deal with, again, eccentricity. And eccentricity we should be familiar with by now is simply the focal length over the major axis length. So in this case, eccentricity will be c over b. So hopefully that's real easy to figure out. Hopefully nothing about that was overly difficult. And with that, let's go ahead and take a look at a couple hyperbola problems. And then we'll actually do some calculus. So for our first hyperbola example, we're going to do the starting to be cliche, complete the square and put it in the right form and find the information and graph and all that good stuff. So we've already done a couple of these, one for a parabola, one for an ellipse. Now we'll try one for a hyperbola now. What if they did not tell us that this was going to be a hyperbola? How would we be able to know? Well, notice that we do have x squared and y squared. Since they're both squared, we know it's not a parabola. Furthermore, notice that the x squared term is positive, while the y squared term is negative. Because they have opposite signs, that's how I know this is going to have to be a hyperbola. That being said, let's go ahead and start putting this into the right form. I'm going to factor a 9 out of the x terms. That'll leave me with x squared. Instead of 54x, I'll go plus 6x. And I'll leave a little space here so I can complete the square. For the y's, there really is no constant to factor out of the y's. However, I will put this minus 1. I'll factor that away. That'll leave me with y squared. I'm not going to write 10y. Remember, I factored out a negative, so it's not going to be positive 10y. This will be negative 10y. Be very careful. That's right there probably one of the biggest errors that I've seen made when dealing with conics. So there's our y's grouped together, and then on the right side I will just have negative 55. Now all I need to do is start completing the square. Here my middle term is a 6. If I take half of that and square it, I'll get a 9. So am I going to put plus 9 over here? No, be very careful. I did not just add a 9. I actually just added 9 nines. So to balance that, I will put plus 81 on the right side. And to complete this square, half of negative 10 is negative 5. And if I square that, that's 25. So should I add 25 to the right side? Again, no. Be very careful. I did not add 25 here. I actually subtracted a 25. And so I will do the same over on the right side. All right, so I'm looking good so far. This will give me 9 times the quantity x plus 3 squared. All good there. And over here I'll have minus 1 times the quantity y minus 5 squared. If I do a little bit of math on the right side, I'll see that that actually equals 1. So I really don't have anything to divide by. At first, that might look like an issue because I can't have a 9 here. I need to have something in the denominator. In the 1, well, no big deal. I can put a 1 in the denominator. But here's how I'm going to resolve this. Instead of having a 9 in the numerator, let me get rid of that. I'll put it in the denominator, but it'll be put down there as a 1/9. You can verify for yourself that I didn't change any values. It's still pretty much the same thing. And I'll do that over here. I'll take this 1, do the reciprocal of it, and stick it in the bottom. And here's my hyperbola equation. A little messy maybe, but it's there. So let's go ahead and find all the information we can. We're going to start with the center, as we should do with every conic. We'll start with the center, and hopefully it's easy for you to see that the center here is simply going to be negative 3, 5. So I'll go ahead and put that on my graph. I always like to graph as I go along. It helps me to see where I should add and subtract numbers. All right, next thing I should do is work on the vertices. The vertices for this, because the x term came first, I know this is going to be a sideways parabola. What's underneath the x is 1/9, and the square root of that is, of course, 1/3. So I'm going to go 1/3 to the left and 1/3 to the right. That'll give me my vertices, and you can see that it's starting to get really crunched up there in the middle, but, you know, it is what it is. So if I add and subtract 1/3 to the x value here, what am I going to end up with? Well, I will have negative 10/3, 5. That'll be the one to the left. And then, of course, I'll have negative 8/3, 5. That will be the vertex to the right. Now, I'm not really required to give the conjugate vertices, but I like to do it anyway. It makes my life easier. I can make that cool little box. Notice that I have a 1 under the y term, and the square root of 1 is, of course, just 1. So here are my conjugate vertices, and based on that, I can make my my box. That box is going to help me, A, find the asymptotes, and B, graph the hyperbola. So that box, while not necessary, could be real helpful. So if I want to find the foci, first thing I need to do is find my C value. And remember that for a hyperbola, c is simply a squared plus b squared, or b squared plus a squared, or however you want to call it. In this case, it will be the square root of 10/9, or if I want to, I can simplify that to the square root of 10 over 9. That is just a shade, or rather the square root of 10 over 3, rather, I should say. And that is really just a shade greater than 1. The square root of 10 is about 3.2. So this is just a little bit greater than 1. And remember, the eccentricity actually does mean something. Because I got eccentricity greater than 1, that's how I know that this is going to be a hyperbola. Anyhow, to find the foci here, I'm going to travel along the major axis. And what I'm going to end up with, if I go the square root of 10 over 3 to the left and right from the center, like I said, it's just a shade over 1. So I'll get a focus there and a focus there. If I want to write these down, that'll be negative 3 minus the square root of 10/3, comma 5. There's one focus. And then my other focus will be negative 3 plus the square root of 10 over 3, comma 5. So I've kind of drawn them there, but there's what they're defined as. So I think we're good. Now, the last thing we really need to do, we should do the eccentricity, and we will. But before we get to that, we really should define the asymptotes here. Now, I'll write the equation for the asymptotes in a second, but what I do know is that my asymptotes will look like this. That will be my positive asymptote. It passes through the center and the corners of this box. And my negative asymptote will be very similar. Again, it'll go through the center and the other corners of the box. So, let's go ahead and write this here. My asymptotes. Well, the first one is simply going to be y minus k, which in this case is 5. So y minus 5. The slope here is simply going to be up 1 over 1/3. And so if I go up 1 over 1/3, that's kind of ugly. Maybe what I should do is just rewrite that as 3. And then I have, of course, x plus 3 for my point that it's going through. My other asymptote will be very similar. Y minus 5 equals negative 3 quantity x plus 3. So there are my asymptotes, my cool little box. And now it's time I can go ahead and draw my hyperbola. I will, of course, go through the vertices, which are here and here. And I will draw it so that it is asymptotic to the asymptotes. That just kind of makes sense. So my left wing, or branch as it's often called, will look like that. And my right branch will look kind of like this. And there is my hyperbola. It's very, very skinny. I knew that it would be because of the eccentricity, but there is everything. Speaking of the eccentricity, let's go ahead and take a look at that real quick. My eccentricity is, of course, going to be my c value, which is the square root of 10 over 3, divided by the length of my major axis, which in this case is just 1/3. And so if we do that, we get an eccentricity of 10. I believe I was saying that the eccentricity was square root of 10 over 3 earlier. That's not the eccentricity. That's just the focal length. But there's my eccentricity. Again, it is greater than 1. I wasn't wrong about that. Eccentricity greater than 1 tells me that it's a hyperbola. Well, with that, let's take a look at one more problem where we're given information and we have to find the equation. And then we'll do some calculus. All right, in our second hyperbola example here, again, we're given some information. We're given a couple vertices, we're given both of our foci, and based off of all that, we need to find our equation. So, let's go ahead and graph what we know. Our vertices are going to be 2 positive 3 and 2 negative 3, and our foci are going to be 2, 5 and 2, negative 5. Clearly, I can tell that this is going to be an up and down hyperbola, so that's going to help me write my equation. Before I do that, notice that I know my center is going to be at 2, 0. That's going to help me out. That means I know that my y squared is not going to have a constant on it, but it is going to come first. And I know that my x is going to be x minus 2. And I'll figure out what goes under both of those in just a second, but it will equal 1 per the standard conic hyperbola form of the equation. So, do I know anything here that I can put on the bottom immediately? Do I know, for example, the major axis length? That I do. That I do. Notice that from here to here, that is going to be my major axis length. It's 3. And so what I'm going to put under the y squared is going to be 9. All right, so far so good. All I need now is to figure out what goes under the x minus 2 squared, and maybe my focus will come into play. See, if I recall that my focus equation is c equals the square root of a squared plus b squared. Now, I know b squared. That's given right there. That's 9. So let me go ahead and fill that in. Also, I know that c is 5. My focal length is 5. So let me put that there instead of c. And I have a squared plus 9. All right. Let me square both sides of this. And if I do that, I'll have 25 equals a squared plus 9. And so clearly, if I subtract 9 from both sides, a squared is 16. I could go a step further and say a is 4, although it's not really necessary to do that in order to do the equation, because that's just a squared on the bottom. However, if I wanted to go through and graph all the rest of this, knowing that a is 4 is very helpful. It tells me that I'm going to have a conjugate vertex here and a conjugate vertex here. And if I want to, that can help me to create my box. And I'll just show this to you as an example. Because the last example, the box was kind of hard to see. So there's my box. If I want to do my asymptote, which I always do, there's going to be one asymptote. This is going to be my negative one. I started with that for no good reason. And here's going to be my positive asymptote. Again, notice that they go through the center and through the corners of this box. So now I can go ahead and draw my hyperbola. It's going to be very wide and go something like this. And over the course of time, will eventually become asymptotic to these asymptotes. But it is very wide, opening up and down. That's how I knew the y was going to come first in the equation. And there we go. So in our next and final example, we'll take a look at finding tangent lines and normal lines to a conic section. So our final problem of this chapter's notes will deal with finding tangent and normal lines to this given hyperbola here at the value of x equals 4. Now, tangent lines we've talked about all year. You should be fine with those. We simply need to find the derivative of the function at x equals 4 and use that to construct a linear equation. A normal line is the perpendicular of a tangent line. That might be a new term to some people. Certainly if you're taking physics, you should be familiar with normal lines. But in this example, we will find the tangent lines, no problem. And then we'll find the normal lines, which are simply perpendicular. Again, not a big deal. So the first thing we need to do is, of course, find the derivative of this function. If we're trying to find tangent and normal lines, we have x equals 4, but we need to find the slope. Actually, we also need to find the y value, but I'll leave that as an exercise to you. If you plug x equals 4 into this equation, solve for y, and I think what you'll get is actually already marked here on the graph. So there are 2 points where x equals 4, and we're going to have to handle both of those. Anyhow, this equation, the first thing I want to do is to clear the fractions out. So I'm simply going to multiply everything by 4. And that will now give me an equation of a hyperbola that does not have fractions. Now this is going to be an easy derivative. The derivative of y squared with respect to x is simply going to be 2y dy dx. We do need to do that implicit thing here. The derivative of minus 2x squared will simply be minus 4x. And the derivative of 4 is, of course, 0. So if we do a little bit of cleaning this up here, what we should find is that dy dx, in other words, the slope of any point on the graph of this hyperbola, is simply going to be 2x over y. And you can do the algebra for yourself and see that that is the case. So for our tangent lines, that will be the slope, and we'll be passing through the points 4, 6, as well as 4, negative 6. All right, so let's go ahead and start with doing the point 4, 6 here. I'm going to do this down here. Our tangent line to this, and let me write tangent here. Our tangent line will simply be, and this shouldn't be too far-fetched, but we'll have y minus 6 equals our slope, 2x over y. So if I plug x and y in here, 2x over y, certainly you should see that would be 4/3. And then x minus 4. That will be the tangent at this point right here. Certainly it is a positively sloped line, and our 4/3 does work. So there's our tangent. If we want to go through and find the tangent line to the point 4, -6, it should be equally doable. That will just be y minus 6 equals, well, if I plug my x and y into my derivative, this time I'll get negative 4/3 x minus 4. And you can verify that the tangent line would in fact be negative. So this does work. All right, so this is the slope for my tangent lines. What is going to be the slope for my normal lines? Now, remember I did say that normal lines are simply perpendicular to the tangent lines. So if the slope of a tangent line is 2x over y, what would be the slope of a normal line? Well, it would just be the opposite reciprocal, negative y over 2x. And so let's go ahead and find the normal lines at these 2 points. At 4, 6, what we should get for our normal line will be y minus 6. And of course, if we plug our x and y in here, what we should get is negative 3/4 x minus 4. And certainly those are opposite reciprocal slopes. So these lines are certainly perpendicular. My normal line to the lower point, the 4, -6, is simply going to be y minus 6 equals positive 3/4 x minus 4. And again, those are opposite reciprocals, so that does work. Now, before I conclude this lesson, there is one more thing I want to show you. We've talked a little bit about eccentricity, how if you know the eccentricity, it basically tells you what kind of conic section we're dealing with. Let me go ahead and show you an animation that displays that quite nicely. So, I would like to talk about eccentricity real quick. Remember that eccentricity is simply c, the focal chord length, divided by the length of the major axis. So I want you to consider what would happen in the following situations. If the eccentricity were 0, if the eccentricity were between 0 and 1, what would happen if the eccentricity actually is 1? And then what would happen if the eccentricity was greater than 1? Those are the cases we need to consider. So, if the eccentricity is 0, the only way that can happen is if the focal chord length is itself 0. And in that situation, what kind of shape do we have? What kind of conic section has no focal length? That would be a circle. Now, as the foci begin to separate from the center and from each other, we're going to find a focal length that's still less than the length of the major axis. So that should tell you if the eccentricity is c divided by the major axis, and if that is less than 1, that tells us that the focal length has to be less than the major axis length. And if that happens, then we have an ellipse. You can see that in the animation that keeps running here. If the eccentricity is between 0 and 1, we have an ellipse. Now, if the focal chord length equals the major axis, we kind of have a weird situation there. And I'll just go ahead and tell you that that would give you the famous parabola. Now, as the focal chord length grows beyond the major axis length, of course, then we're talking about foci that are outside or external to the conic, and that's why an eccentricity of greater than 1 tells us that we have a hyperbola. So hopefully these running animations here kind of explain it in a visual sense. Feel free to write them down and compare the focal length to the major axis length for various conic sections and see for yourself that everything I just said is true. And it's been a long lesson. We've learned a lot about conics, about parabolas and ellipses and hyperbolas, about eccentricity, major and minor axes and vertices and conjugate vertices and directrixes and latus rectum. That was a fun one. All kinds of stuff. It's a lot of things. In some courses, this one lesson takes an entire chapter. So it's no easy task that you have here. as you continue on to your assignment. But remember everything that you've learned here. Remember your visuals. Your pictures will help you. And I wish you good luck.